So, but this question you should have an idea. So far, when we talk about dynamics, what I mean in general, as you see, is things evolving in time. That's what dynamics means. So dynamical systems means studying things that evolve in time. So for game theory and other things like that, we had, payoff functions, other things in physics like electromagnetic fields and things. These all have clear time evolutions. Right? Even in biology, you have populations that evolve in time. But in our universe, in cosmology, it's not so simple. And the reason is the following. So let me ask you, how many dimensions do we live in right now? Not string theory. In general, how many dimensions do we live in? 4. So what are those 4 dimensions?
3 space and 1 time.
Okay. So the claim is that we live in 4 dimensions, 3 space, 1 time. But we don't just live in space, and we don't just live in time. We live in space-time, so it's 4 dimensions. So it's not just space, it's actually called space-time. And this was actually not Einstein's original idea. It was actually due to, if you can believe it, Poincaré again. And related to Poincaré was, does anybody know? It was not a Greek fellow. It was Minkowski. And then Einstein. Yeah. And then Einstein kind of took the ideas and put it forward. But the idea is that you cannot separate space and time. They're one entity. So if you want to picture our universe as a 4-dimensional manifold, then any event in our universe is labeled by 4 coordinates. x1, x2, x3, and then a time coordinate. So it's space-time. The point is you cannot separate these two. They are on equal footing. That gives you a problem when you're trying to understand dynamics, because then what does it mean for something to evolve in time? You see the problem. So the way you do this, in our universe, we want to understand the dynamics of our entire universe, how it's evolving. It's a problem because it's space-time. So how do you talk about something evolving in time? Well, what you do is, and I'm skipping about 2 months of general relativity lectures here, but what you do is you take your 4-dimensional universe and you apply what is called a foliation. And what this foliation does is it takes 4 dimensions and splits it into 3 plus 1. And so 3 spatial coordinates and 1 time. So in other words, you take your 4-dimensional structure and you break it up with the preferred time-like structure. I won't do it. And you have a bunch of 3-dimensional slices that you are evolving in time. So this would be a 3-dimensional slice at time t is equal to 0, t is equal to 1, t is equal to 1. So now your dynamics of the universe are about 3-dimensional surfaces evolving in time. And this is because of this 3 plus 1 split. Okay. So in here, this is governed by the Einstein field equations, which you don't have to know, I'm just writing it for completeness. And the main point is that on the left side of these equations, you have curvature terms. And on the right side, this TAB is a matter term. So the idea is that you have matter in the universe, like physical matter, like radiation, dust, etc., that induces curvature in the space-time. In the 3 plus 1 picture, you have curvature that's evolving in time. So that's how you talk about dynamics. So, but these are 4-dimensional equations. How do these translate over to a dynamical framework? So the idea is to to get dynamics, there are many ways. This is not a unique way to go from this picture to this picture. It's a convenient way to do it. To get dynamics, what you use is something called the orthonormal frame formula. And I will not also go into this in too much detail because I don't want people to start throwing things at me. But the idea behind this is that if you assume that on large scales, the universe is what we call spatially homogeneous. And I'll explain what this means in a second. Then, the Einstein field equations can be written as a nonlinear system of first order ordinary differential equation, a dynamical system. Does anybody know what I mean by spatially homogeneous? Yes?
That everything looks the same from everywhere.
Almost. Just isotropic. What do I mean by homogeneous? So I mean, that's a good point. So when I say something is spatially homogeneous, I mean that it's translationally invariant. So if I have something like this, like a circle or a sphere, and I take 2 points, and I move the 2 points, the sphere still stays the same. So I can translate, so this is invariant with respect to spatial translation. So on our largest scales, our universe is invariant with respect to spatial translation. It's homogeneous, and it's isotropic as well, but that's for another time. Okay? So the main point is the following. You can take these tensor equations that are actually 10 nonlinear, coupled, hyperbolic, partial differential equations. They have no solution whatsoever. And you can reduce them to a dynamical system if you assume that the universe is spatially homogeneous on logic. Because you see, if I tell you that the only thing that's evolving is time, that's what it means to be spatially homogeneous. Nothing is changing in space, it's only changing in time. Yes?
Two questions. The first one, did Einstein actually do this equation himself?
Yes. Under 10 years.
10 years?
1905 to 1915.
So then he didn't know how to solve this, but he interpreted it?
So there's a funny joke behind this. Einstein, in the process of 10 years of deriving these equations, spent many years going to talks where he was giving people kind of previews of what he was trying to do. And in one of his latest talks, around the 1915 mark, David Hilbert was sitting in the audience. Hilbert figured it out, what Einstein was getting at. And Einstein knew that Hilbert knew what he was going to do. So he rushed on, and they had a race between the two of them, actually. Hilbert figured out what Einstein was trying to do in 10 years in 1 hour. That's how smart David Hilbert was. So he figured out these equations. They are his equations. But then he concluded in his paper, except for the most trivial cases, these equations cannot be solved. Lo and behold, 2 years later, Schwarzschild comes up with a solution of these. So they're extremely complicated to solve. But you can do this, and you can get a dynamic system.
Second question.
Yes?
So you said for the sphere one, you have 2 points and you move them, they're the same?
The sphere doesn't change.
So what is that for reality for space? You're saying if I take any 2 points in space and I move them anywhere?
The universe is on the largest scale. If you see a picture of the cosmic microwave background, for example, you can take any 2 points in the night sky, but the universe doesn't change its structure with respect to rotations or translations of those points. That's it. So our universe is a very geometrically special. Okay, so but what are these equations? So when you apply this formalism, as I said, the field equations become a dynamical system. So you get three equations. The first equation has a special name for it because it was derived by an Indian physicist for a change. His name was Ray Chaudhuri. And his equation is called Ray Chaudhuri's equation. And I'm not saying this because I'm obviously biased. I'm just saying that it is actually the most important equation in cosmology. I will say that. Okay. There are many non-Indians that will agree with me on this. Okay, and it goes like this. So you get theta prime. I'll explain what these variables are. So prime means d by dt, as usual, okay, is equal to minus 1/3 theta squared minus 1/2 mu plus 3p plus capital M. I'll explain these symbols in a second. I just want to write down the equation. So you get Ray Chaudhuri's equation. You get what is known as the Friedmann equation. Or constraint. And that looks like the following. So 1/3 theta squared is equal to minus 1/2 capital R plus mu plus lambda. You get an energy conservation equation energy density slash conservation equation, which goes like this. So mu dot, I shouldn't put dot, I'm using prime. So mu prime is equal to minus theta mu plus p, and then you get the longest of the equations, which is the curvature evolution equation. R prime is equal to what? 4/9 theta cubed plus 2/3 mu plus 3p minus 4/3 theta lambda minus 2 theta mu plus p. And that's it. So you get three dynamical equations, just like we have for other systems, and one constraint. Now, what are all these things? I have no idea, I just made them. I'm joking. But the point is, as you can see, using some formalism, which I'm asking you to take my word for, or you can look up the paper, it's very good. You can reduce these tensor PDEs to a bunch of ordinary differentials, just like we had for everything else we did. Now, what in the world are these symbols? I will tell you. Theta is what we call an expansion scalar. It tells you how the universe expands or contracts. If the universe can expand, it certainly can contract. That's what theta is. So Ray Chaudhuri's equation tells you the dynamics of the expansion rate or contraction rate of the universe. Mu is the energy density of matter in your universe. P is the pressure, so the matter pressure. What else? R is the three-dimensional curvature of the spatial slices I drew there. And it evolves in time. So you have an R prime equation as well. And then lambda is known as the cosmological constant. It It is one of the fundamental constants of nature, of our universe. Does anybody know what it is, the number?
Oh,
You don't have an idea? It's not 5. It's actually a very small number. It's 10 to the minus 122. About.
was it this or was it?
The cosmological constant represents what we call dark energy. Well, that's the belief anyway. And dark energy is responsible for the accelerated expansion.
You think this would be the longest time?
Yes.
Right there saying that.
So Einstein,
And there isn't.
right, so Einstein, so this lambda here, this capital lambda, is responsible for the accelerated expansion of the universe, the dark energy. Einstein introduced it into his equations by accident and thought it was a mistake at first. But then it was later on discovered that actually you need this. So it was his biggest blunder, as he said, but the most useful one. So is that clear so far? So one governs the expansion of the universe. You have things that talk about the matter and pressure of the universe. R is the curvature, and lambda is the cosmological constant. Okay. So, but as we've been doing with everything else, we have a constraint. So I can use the constraint to eliminate one of the variables. It's the same thing. There's nothing, actually this is, in some sense, more easy to deal with than the biological systems because as of now, as you'll see, we only really have one free parameter. In the SRS model, we have like 7 of them, no bit. But it's much easier. So let me do that first. And there's a hidden surprise when you use a dynamical systems method like this, and I'll tell you what it is. But I have to have it. So, can anybody quickly look? I erased the theta prime equation now. But just like in dynamical systems, I need one equation for every variable to have a closed system, right? I have not accounted for one variable. I'm missing one equation. Can anybody tell me what it is? Look carefully. Do I have an equation for theta? Do I have an equation for mu? Do I have an equation for r? Lambda is a constant, so whatever. What am I missing? Pressure. How do I take care of that? Any fluid mechanics people in here? Do you know? From atmosphere? No? No, I don't want to. Does anybody have an idea? How I can talk about pressure? I'm missing pressure. No. Okay. So, there's an assumption, which is actually a pretty good assumption. We can assume that the matter in the universe is what we call barotropic. That means that the pressure is proportional to the energy density. And this, how do I change a proportionality to an equation? I have to introduce what? Constant, right. So to fix this, I will assume that P, which is the pressure, is given by some constant W times mu. And that will allow me to close the equations. And in particular, what is this W? We call it an equation of state. And if you take courses in fluid mechanics, you will see this. Equation of state pressure. And this W, which is a dimensionless number, describes the type of matter you could have in the universe. In particular, we assume that W strictly is between -1 and 1. And there are some examples of what values of W can be. So, in particular, so some examples. If W is equal to 0, that means your universe is filled with dust. Just straight old cosmic dust. If W is equal to -1, this means you have a second cosmological constant, which is quite possible. If W is equal to 1/3, it means your universe is filled with radiation. There are some more exotic states. If W is equal to minus 1/3, these are what you call cosmic strings. And the most extreme case, on the other end, is if W is equal to 1, this is what we call a Zeldovich fluid, or a stiff fluid. So this is valid at very early times in the universe. So now we have accounted for, and this is the only free parameter that will show up in our equation, this W. So now we have accounted for all the variables. Now I will use the constraint to eliminate normal equations. And this is all fluid mechanics theory. As I said, I'm skipping about 3 textbooks worth of courses for this 30-minute lecture. But it's okay. We want to understand using what we know. So.
Is this size or
Sorry?
size equation that are created?
Okay. So I will now use the Friedmann equation to eliminate mu, just by choice. I don't like mu, I will eliminate. And as a result, you get 2 equations. So the Raychel's equation becomes the following. 1/4 minus r minus 3rw minus 2 theta squared minus 2w theta squared plus 6 lambda plus 6w. And the r prime equation is so simple, it's laughable actually. And you don't expect it actually. Watch how simple it is. It's minus 2/3 r theta. Yeah. It's such a surprise when you derive it, and this just comes out as one term. Very nice. So just like our other examples, the entire evolution of the universe on the larger scales comes down to 2 ordinary differential. Okay. I skipped a lot of stuff, obviously, but this is the answer that we're interested in. Any questions? Oh, so that's our dynamical system, and it has one free parameter, which is the. So you can tell now stability will depend on what W is. And I should make this point that you can have mixes of these two. So you can have intermediary states like 4/3, which is like radiation plus dust or something like that. You can have mixes. Okay, so that's our dynamical system. So now what is the first step when we give, because I don't believe that these can be solved. I tried, it doesn't work. So, what is the first step?
Isn't W negative 1 and 1?
It is. Oh, you're right, I'm thinking of something. Try 3/4, so, yeah, okay. Okay. Or 4/5. You can have mixes of it. Any number between -1. Okay, so what is the first step? Equilibrium. Equilibrium. As usual. Now you can see, actually, find the equilibrium points is actually the easiest. It turns out in the cosmology case compared to the biology case. That's because biologists tend to overdo everything. But also it's because the only way equation 2 can be 0 is if r is 0 or theta is 0. There's nothing to do here. If r is 0, set r to 0 in all of these, you get a solution for theta. Step 2, set theta to 0. Set theta to 0, you'll get a solution for r. So it's extremely simple to find the equilibrium. So let's see what else. claim there are 3 equilibrium points. Okay. So, and this is the surprise about this method. So when I told you before that the Einstein equations are impossible to find closed form solutions for, it turns out actually, unlike our previous examples, the equilibrium point actually means something very significant to this dynamic. And in fact, the surprise is that the equilibrium points are solutions to the Einstein equation. They just aren't random points like in biology and game theory and stuff. They actually are solutions to the field. So in some sense, there are new ways to find solutions to Einstein equation using this orthonormal frame formalism. So what are they? So one equilibrium point. So I'll call this equilibrium point 1, or just P1 maybe for short. So as I said, the simplest thing to do is to just set in turn theta to 0 and y to 0 and see what happens. So if you set theta to 0, so remember I'll call it theta star or star. So set theta to 0, and then you solve the R equation. What do you get? You get 6 lambda plus W lambda over 1 plus 3. Now, let me ask you, what is significant about this solution? What does it mean to have theta equal to 0?
R is constant.
Say?
R is constant.
No, theta is equal to 0. Exactly. That's the key point. And so if it's, something is not expanding or contracting, what is it by definition?
Static.
Static, that's right. Very good. So theta is equal to 0. Remember, theta is the rate of expansion and scalar. So if it's not expanding, it's static. So the first set of equilibrium points represent static universals. And now it depends on the sign of R, how you subclass these static universals. So let me ask you a geometry question. If I have something that is spatially homogeneous, and actually I also made another assumption which Spiros alluded to, but I actually didn't admit it at the time. Not only am I assuming spatial invariance, but I'm also assuming rotational invariance. So, if I have some shape, easy geometry question. If I have some shape and it's invariant with respect to spatial transitions and spatial rotations, what are the only 3 possible geometries I can have? Sphere is one of them, in 3 dimensions. So, what are the only possible 3-dimensional geometries I can have? Sphere is one, planar is another. Perfect. Why did you say hyperbolic? Okay. Right. There's only 3 possibilities. You can have a sphere or spherical geometry. You can have a hyperbolic geometry, which is like a saddle. Do not get confused, I don't mean the same hyperbolic as equilibrium. Or you can have a planar geometry. Only 3 possibilities. In the first case now, is the curvature positive, negative, or 0 for a sphere? Positive. So R would be greater. For a hyperbola or a saddle, is my curvature negative, positive, or 0? And for a plane, is it flat? Yes. So not only do the first set of equilibrium points represent static universes, but they have a subclass now depending on the sign of this. So, for point 1, if R star is greater than 0, these are static spherical universes. If R star is less than 0, these are static hyperbolic universes or negatively curved universes. And if R star is equal to 0, you have static flat universes or just plain old Minkowski space-time of special rays. Static and flat. Now, what is the only free parameter in R star? W. And W goes between -1 and 1. So depending on the sign of that, or the sign of W, we will have these types of cases. So let's see what we have. And in fact, the case where R star is greater than 0 and it's static, this has a special name. It's called the Einstein static. It's actually one of the first solutions he found. Yes? Static and flat, if you can imagine. I meant to say flat. No. Sorry, I lost my interest in writing. Okay. So let's see. Let's analyze this equilibrium point and see what we have. But in general, the first equilibrium point represents classes of static universes, because no matter what theta is equal to 0. So, if R star, I'll just write out R star, is equal to 6 lambda plus W lambda over 1 plus 3, 0. What is the only way R star can be less than 0? As you can do the analysis, it means that 6 lambda plus W lambda over 1 plus 3W must be less than 0. Now, as I said, lambda is just a constant. It's positive 10 to the minus 122, but it's a positive number. And W goes between -1 and 1. So the only way this can be negative, as you can show, is if W is strictly between -1/3 and 1. So, for any matter where W is -1/3 strictly less than and up to 1, you'll have R star less than 0. Greater than 0. Sorry, I'm doing the close case. So there will always be an Einstein static universe equilibrium point if W is between -1/3.
Is that because the top doesn't matter at all because it's just one number? So you're facing it on the denominator? Yeah.
Essentially, yes. But you can just do the algebra of the inequality as well. Question.
So, R is equal to that
Yes. So I was doing the closed case, but I wrote the wrong sign. Okay. Now the second case, R star less than 0. So when do we have static hyperbolic universes? Is when 6 lambda plus W lambda 1 plus 3W is less than 0. And this is kind of more or less the opposite, right? So in this way, this will only happen when W is strictly between -1 and -1. You'll get that. And the final case, you'll have a Minkowski or a flat universe. With what? See it? Did you see the answer? Oh, okay. And R star is equal to 0 if this is equal to 0, and that will only happen in the extreme case when W is -1. What? You did it. That's it. This is a -1, not a minus blind and box.
Perhaps if W is equal to -1/3.
You have have singularities. But I do not want to talk about this at this juncture, because I can feel the tension in this room right now. I do not want to. Actually, it's a very important case. What you brought up, you see the curvature blows up, goes to infinity. So that's an example of a cosmological singularity. We talked about that. Okay, but is everybody clear on this? So it's the same thing. It's actually easier than the biology example. I have my dynamical system. I found the equilibrium point. And now I just look at the sign to see what I have. And the sign depends on the prime. Okay, that's the first set of equilibrium points. In 1 minute, I think I can tell you the second set. Because really there's one equilibrium. So these set of equilibrium points happen when I set theta to 0. Let me do the other one now, set r to 0. The equilibrium point. No, I had to do it now on Wednesday. I was going to do it, I thought I'd have time, but I did not. Probably because you asked so many questions. No, I thought I had time. Okay, so now we will set r to 0. And what does it mean if I'm starting only with solutions of r to 0? What type of points are these? So, I've not set theta to 0, just set r to 0. So they're flat. So these are flat numbers. To be proper, I should say spatially flat. Because I criticize other people when they do not put spatially, so I should switch. And what happens is you get the following equilibrium. Theta star, r star. If you set r to 0 in that equation and you solve for theta, you get the following. Very easy. Square root of 3, square root of 1, and theta. And actually, we can write down the second one as well, because it's just the minus of this. So there's 3 equilibrium points in total. The Einstein static universes and these flat universes. And these are also solutions to the field equations as well. In fact, these are what we call de-Sitter. And now you see theta is not 0, it has a number. If it's plus, so theta is equal to plus square root of 3 square root of lambda. These are expanding. I'll just put ds for de-Sitter. And obviously if theta is equal to minus root 3 root lambda, these are contracting. And I literally mean this. So if you have 2 observers in these universes that are moving in this universe, when I say they're expanding, I literally mean they're expanding apart. So one goes like that, and one goes like that. And the rate of this divergence is what you call theta. But you can go the other way too. So you can start, if the universe is contracting, as these observers are moving along these lines, they will eventually reach the same. 1 second, I'll get you. Okay. So these are the 3 equilibrium points. Now, which I must say for Wednesday, what is now the next step? So we will now analyze now, based on the eigenvalues, which of these points are stable, unstable. That's what we do. Any questions? It's the same thing. But this is much, much more interesting than anything biology does. I know. I've given up trying to edit and find out.